Welcome to Get Your FRQ On. This question is from the 2007 B exam. It is question 5 and it is not calculator active. For part A of this question, we are asked to sketch the slope field for a differential equation dy dx equals 1/2 x plus y minus 1. We are given a graph with 9 points on it, so to fill in the slope field, we're just going to take whatever the coordinates for the 9 points are. We're going to evaluate dy dx using that coordinate, and then we're going to sketch a tiny little line segment that has that approximate slope. And when we do that, we get a slope field that looks like this. All right, for example, if x is -1 and y is 0, 1/2 times -1 is -1/2, plus 0 is still -1/2, minus 1 is -3/2, so notice that this little red segment here has slope approximately -3/2. If we check it at the origin, 0 plus 0 is 0, minus 1 is -1. Notice this little segment here, slope is about -1. These little segments don't have to be perfect. Basically what they're looking for is, are they accurate? In addition to what we mean by accurate is, does one look like it has slope approximately 1? But also, if you have a segment whose slope is 1, does it appear that slope that you drew is more than another one, which is supposed to have slope like 3/2? So they have to be fairly accurate. They don't have to be perfect, but they need to be accurate, and they need to be relatively accurate between the different points. Whichever one is the most should be the steepest segment. All right, so we get a slope field that looks kind of like this. In part B, we're asked to find the second derivative of y with respect to x and then describe where in the xy plane all of the solution curves would be concave up. All right, so first, in order to find d2y dx2, we're just going to take the original differential equation dy dx and find the derivative of that. If we differentiate 1/2 x plus y minus 1, we're going to get 1/2 plus dy dx. But we already have an expression for dy dx that's given in the question stem, so we have 1/2 plus 1/2 x plus y minus 1, which simplifies to 1/2 x plus y minus 1/2. And then the second part of this question, where in the xy plane will all solutions be concave up? All right, well, the solution curves to the given differential equation will be concave up whenever the second derivative is positive. All right, well, that just means 1/2 x plus y minus 1/2 has to be greater than or equal to, or greater than 0, not equal. That's a fairly easy linear inequality to solve. If we solve that for y, we get y is greater than -1/2 x plus 1/2. So where will the solution curves all be concave up? Well, that'll be any point x comma y in the plane such that y is greater than -1/2 x plus 1/2. In part C, let f of x be a solution to the differential equation such that f of 0 equals 1. Does f have a relative minimum, a relative maximum, or neither at x equals 0? And then justify your answer. Right, so let's assume what we are supposed to assume. Assume that f of x solves the given differential equation and that f of 0 is in fact equal to 1. All right, well, dy dx at the point 0, 1 turns out to be 0. Okay, well, that's good news, right? The derivative is 0 there, so we have either a relative minimum or a relative maximum. All right, so f definitely has a critical point at 0, 1. To determine which type, we can evaluate the second derivative, which we already found. All right, so evaluate the second derivative at the point 0, 1, and we find that d2y dx2 at 0, 1 is positive 1/2, which is greater than 0. So the concavity there is positive. It's going to be concave up, which means that f of x has a relative minimum at 0, 1, because its derivative is 0 there and it's concave up, so it's at the bottom of that little dip. So f has a relative minimum at 0, 1. Part D, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, algebra gets a little tricky here, so I'll try to go a little slow. Assuming that y equals mx plus b solves the given differential equation, then the derivative of mx plus b would have to match dy dx. Okay. The derivative of mx plus b is just the slope of the line, that's just m, but that would have to equal 1/2 x plus y minus 1, right? But notice up here we have an equation for y is just mx plus b. So if we substitute the y equals mx plus b in for y, we now have m equals 1/2 x plus mx plus b minus 1. All right, now there's only m's, x's, and b's. All right, so if we start to simplify this, m equals 1/2 of x plus mx plus b minus 1 implies that 0 is equal to 1/2 of x plus mx plus b minus 1 minus m, which further implies that if I have 1/2 plus m times x, I'm really just factoring out the x from those first two terms, plus b minus m minus 1/2, then I get just an equal equation. And then this is where it gets kind of tricky. It's not obvious here, but we have to equate the coefficients. The line 0, or the value 0, corresponds to the line whose slope is 0 and whose y-intercept is 0. Right? Think of that as 0x plus 0. If I do that, then the equation 1/2 plus m times x plus b minus m minus 1 equals 0 can be solved by equating the coefficients. 1 plus m has to equal 0, which means m is equal to negative 1/2. And then b minus m minus 1 has to equal 0, which means that b is equal to 1/2. Right? We can substitute our newfound value of m into that second part, which will help us solve for b. All right, so the values of m and b that we are looking for are negative 1/2 and positive 1/2, respectively.